Good afternoon. We're looking at shape of molecules and hybridization. The two topics help us to achieve a similar thing. Okay, with the help of shape of molecule, you can determine the bond angle, and then you can tell if a molecule is linear, if a molecule is trigonal planar, if a molecule is trigonal pyramidal, if a molecule is tetrahedral in shape, and then you can tell if the molecule is having lone pair or bond pair, the number of lone pair and the number of bond pair. I'm sure we're following. Okay, now then they are explaining in a moment of time very quickly. Now coming to shape of molecule, it helps us to know the total electron pair. That's the TEP. TEP means total electron pair surrounding a molecule or a compound, and basically total electron pair is equals to LP plus BP. LP means electron pair repulsion. This helps to basically minimize electrostatic repulsion around the molecule. This is what VSEPR theory aim at achieving. I will be explaining that later. Now, in the case of shape of molecule and hybridization, we know that hybridization has to do with the blending or the mixing of two pure atomic orbitals to form the same to form a new hybrid with the same energy level. What does that mean? You have two pure atomic orbitals such as s orbital, two pure atomic orbitals such as p orbital, or two pure atomic orbitals such as d orbital, and then forming a new hybrid entirely that can either be sp, that can be sp2 or sp3 or sp3d or sp3d square, and so on and so forth. This is what we call a new hybrid. But before the new hybrid, two or more pure atomic orbitals came together to form a new hybrid. Okay, I'm sure that's very clear. I'm sure that's very clear. Now, when you look at the shape of molecule now, we want to quickly look at some few things because of time. Now, the few things we'll be looking at or considering. Now, we have, we look at the linear shape, we look at the tetrahedral shape, we look at the trigonal shape, and all that. Now, let's quickly look at this very quickly. I'm looking at both beryllium chloride. This is beryllium chloride. For a beryllium chloride is linear shape, right? Now, how do I know the bond pair and the lone pair? Obviously, since it is linear, the bond angle is going to be 180 degrees. Students, is that clear? The bond angle will be 180 degrees. Now, the first thing to do is to draw. We call it Larry structure. Draw 6, that's 8. Hello, are you with me?
Yes, sir.
This is 8. And then count here. You have what now? This is 2, 3, 4, 5, 6, 7, 8. So beryllium chloride. The total available electron is 16. Are the 16 used? In the make of beryllium chloride, you can see now that the whole thing is formed. This is an octet structure for chlorine, and beryllium was able to form its duplex structure, and this is an octet structure for chlorine. So this is for chlorine, and what's going to be, since it is this way, it is linear, what's going to be the hybridization of beryllium chloride? Obviously, the hybridization is going to be XP. It's going to be what? XP. It's going to be XP. The bond angle, it will be 180. Now, we come to the something like this, we come to CO2, SO2. It can be so confusing to students, so confusing to students. This can be so confusing to students. Here you have CO2, here you have SO2. They are not of the same shape, but they are going to have the same hybridization. So let's quickly find out here. Here, we want to know the number of bonds, the number of lone pair, and the number of bond pair. The bond pair actually talked about the one that takes part in the bonding. That's bond pair. That's why it's called shared pair. While the lone pair is the one that do not take part in the bonding. Okay? Now, so we have this, and then you have something like this. Then you have something like this. How do I know? How do I CO2, and CO2 carbon valence is 4, and then this is 8. This is 6 times 2. So you have 4, you have 12, and then you have 16. And then look at it carefully. Look at it carefully. Now here you have 4 bond pair, and how many lone pair? 4 lone what? Lone pair. 4 bond pair. How did I get that? How did I come about that? Because each of these represent 2 electrons. 2 electrons, 2 electrons, that's 4. 2 electrons, that's 6. 2 electrons, that's 8. And you have total of what? 16. So count again. 1, 2, 3, 4. 1, 2, 3, 4. So a pair, that's 1 lone pair. A pair, another lone pair. A pair, that's lone pair. A pair. So together you have 4 what? 4 lone pair, 4 bond pair in this. And no doubt, this is linear. So carbon dioxide is also linear. Carbon dioxide is also linear in shape. But the bond angle is not going to be XP, despite it's linear. The reason is this: there are 2 double bonds, so that makes the hybridization sp2. That makes the hybridization. I'm sure that's very clear. So don't think because I said beryllium chloride we did was sp, this will also be sp because it's linear. No, you need to also check the bond angle there. It's going to be sp2, but it's linear. Okay, we look at SO2. We look at SO2. SO2 is a little bit different in this case. Now SO2, we have something like this. We have something like this. Okay. Yes. And then you have something here. Okay, how do I know? It's like this. Oh, it's quite simple. So look at it quickly. A sulfur is 2A6, that's 6. And then this is 6. And then you have 6 times 2. You have 6 electron. You have 12 electron. And that's 18 what? Electron. That's what? 18 electrons. So want to know how many are used during the bond and how many are not used. The ones that are not used are called the lone pair. So you have 1, 2 used, 1, 2. How many now? That's 4. So 2 times 4, that's 8. That's 8 are used. So there are 8 electrons that are used. That's 4. 4 what? 4 bond pair. 4 what? 4 bond pair. How many lone pair? 5 lone pair. How did I get 5? How did I get 5? 1, 2, 3, 4, 5. Now let's not see if it will give us a total of 18. 10 plus 8 is what? Beautiful, beautiful. So the shape of this now is known as bent shape. It's known as what? Bent shape, like water. Similar shape as water, bent shape. So you find the number of lone pair here. Okay, quickly. Again, what's going to be the hybridization of the one we just did now? The hybridization of SO2 is sp what 2. Please take note of that, very important. Now that takes us to ammonia. Ammonia, if you draw the Lewis structure, what I call it, Lewis structure, you have something like this. Okay, now, but don't forget that SEPR theory aim at minimizing electrostatic repulsion. So I can readjust this diagram going by this. So I will have yes, rather than doing it in this manner. Okay, in this way now the bond angle of the SO2 we finished is 109. That's the bond angle. And it should be noted by my audience who are listening to me and the students here that the more the lone pair, increase in lone pair brings about progressive decrease in the bond angle. Please, you need to note that down. That the increase in lone pair brings about decrease in the bond angle. Can I demonstrate that to you? Or okay, let me demonstrate that. For example, methane has a bond angle of 109.5 degrees. It has no lone pair. The lone pair is 0. It has 4 bond pair and no lone pair. But look at water. Look at ammonia. Ammonia has 1 lone pair and 3 bond pair. The bond angle is 107. But look at water now. Water is having 2 lone pair, but the bond angle is 105. Can you see the statement? With this example has been able to validate the statement I made, that the more the bond angle, the more the lone pair, the lesser the bond angle. Okay, let's come back to what we have here. Okay, so this is the Lewis structure. The next thing is to determine the total available electron around the central atom. Okay, doing that, you do this, please. Okay, ammonia is 5. The valence electron, I'm talking about valence electron. So you have 3. So there are 8 available electrons in ammonia. And each of these things represents what? Electron. So there are 3 bond pair and 1 lone pair. Since only 6 are used and there are 8 available electrons. Okay, so the bond angle here is 107 and it has 1 lone pair. It has what? It has what? 1 lone pair. Now what's going to be the name of this? What will be the name of this? This is going to be called trigonal pyramidal. Please let me help my audience to distinguish between ammonia and boron trifluoride. They both have the same 3-3. How come this is trigonal pyramidal and this is trigonal planar? Let's quickly look at it as my audience see the difference between ammonia and boron trifluoride. Okay, so for the Lewis structure of this is B, which is the central atom. You have the fluorine, you have the fluorine, you have the fluorine. Okay, and then you have this way. Okay, going to the SEPR theory now. The SEPR theory is to minimize electrostatic repulsion, the repulsion. So to minimize the repulsion, the shape will change. The shape will be something like this. So the orientation will now be at 120 degree, 120 degree, and 120 what? Degree. Now, I'm sure that's quite clear. I'll be running on soon. Now you have the pH3. So in this case now, boron is 3, the valence electron, and this is 7 times 3. So 3 plus this, that's 24 electron. 24 available electron. There are 24 available electron around boron trifluoride rather. And let's see, the 24 available electron are being used during the bonding. Look at it. Look at it. That's 8. That's 8. That's 8. 8 times 3. That's 24. There is no lone pair in boron trifluoride. Hence, it is trigonal planar. It is trigonal planar. It's not going to be the same thing as ammonia that has a lone pair and it's called trigonal pyramidal. So we see that there's difference between ammonia and boron trifluoride. I'm sure that's clear to you all. Do we know the difference now?
Yes, sir.
Okay, now in closing it completely, we must note this. Since we have said that total electron pair is equals to lone pair plus bond pair. Now we must note this in closing, that lone pair are greater than lone pair bond pair, and that lone pair bond pair are greater than bond pair bond pair. So this ends the class. Now understand the hybridization again. The hybridization for the organic compound, for all unsaturated hydrocarbon, they have sp3 hybridization, all saturated hydrocarbon. For those of you writing, if you see methane and you are asked what is the hybridization of methane, you should know that it's going to be sp3. The reason is not far-fetched. There is no pi bond in methane. Alkane generally do not have pi bond. What are pi bond? They are bonds that are formed by lateral overlapping of p orbital. Okay, they are weak covalent bond actually. So now, coming to this, the alkane, the unsaturated hydrocarbon, the hybridization is sp2. Why? Because in the 2pa, 2py, and 2pz, the Z here is unhybridized, and that's the lone pair. Alkene has just one lone pair. That's the 2pz. It's not being hybridized. So you have sp2 in the hybridization of the unsaturated hydrocarbon, the double unsaturated. Then the last one, to close the class, you have the alkyne, that the triple unsaturated. You understand? In your 2px, your 2py, your 2pz, because we know that carbon form a bond not at the ground state but at the excited state, because at the ground state there are only 2 unpaired electrons in carbon. So it is at the excited state we have 4 unpaired electrons, and we need minimum 4 unpaired electrons for bonding to properly take place in that. So at the excited state, what happened? The 2px, the 2py, the 2pz, which of them is hybridized? Only this, the 2pa. 2py is unhybridized and 2pz is unhybridized. Hence, we can say that the triple saturated unsaturated are 2 lone pair. What are the lone pair? 1, 2. This is sigma bond. Oh, I said lone pair. I'm talking of pi bond rather. This is pi bond, this is pi bond, and this is sigma. And these 2 pi bonds are the ones that are unhybridized. The sigma bond is the one down. So you can see now that 2px unhybridized. So the hybridization for unsaturated hydrocarbon, that's the triple bond, is sp. That brings us to the end of the shape of molecule and hybridization. Thank you.